So, once again, I welcome you all to this session, and in this session, we are going to discuss the third case, that is nothing but a shaft subjected to combined loading. Okay, and in the previous lecture, we have discussed about the shaft subjected to the twisting moment and the bending moment. And in today's class, we are going to discuss the case which is the third case, that is nothing but a shaft subjected to combined loading. Design of a shaft subjected to combined load, that is twisting and bending moment. And since in the earlier classes we have discussed about a shaft subjected to the twisting moment and bending moment. Okay, so today we are talking about the combination of these two. So what happens when a shaft is subjected to the combined loading? Then due to torsion, the shear stress will produce in a shaft. Okay, so due to torsion, so shaft subjected subjected to combined bending, combined bending and twisting. So due to torsion, shear stress, that is nothing but a tau, will be produced in a shaft, produced in a shaft. And in the earlier classes, we have discussed the formula for the shaft, that is nothing but T is equals to pi by 16 into dq. And then hereafter you can find the value of tau, that is nothing but the 16t upon pi dq. Okay, this is the capital D. This was the case when a shaft is subjected to torsion, and when a shaft subjected to the bending moment, and due to bending what happens? Bending moment, due to bending stress is produced, which is denoted by sigma b, isn't it? Yeah. And if we call the formula of a bending, that will be equal to m equals to pi by 32 into sigma b into d. And so from here, that sigma b will be what? 32m upon pi d cube. So this is my equation number 1, and this is equation number 2. And since we have torsion equation, that is nothing but torsion equation, and the equation was something like this, that T upon J is equals to tau upon R is equal to g theta upon L. And so from here what will happen, this tau is equals to g theta upon L into R. And since from this equation tau is directly proportional to R, it means what? Shear stress is directly proportional to the radius of the shaft when it is subjected to torsion. Okay, from this equation we are getting this. Okay, and for same as it is for bending equation, that the equation was something like this: sigma b upon y is equal to m upon I is equal to E upon R. And so from here this equation is quoted upon sigma b upon y is equal to E upon R. And so from here sigma b is equal to E upon R into y. Yeah. And so from this equation what will happen? This sigma b is directly proportional to y. What is this y? This y nothing but in the theory of flexure structures we have studied that when we move far away from the neutral axis to outer surface, that the maximum bending stress is developed, and at the same time this equation shows that the radius of a shaft when it is subjected to torsion increases the shear stress. That is, the shear stress directly proportional to a radius of shaft when it is subjected to torsion. So from these two what happens? This is nothing but the y. From these two equations we have seen that for a shaft both the things, that the shear stress and the bending moment is maximum at the outer surface, and so we can consider this system as a biaxial stress system. So let me draw the figure, then you can easily able to understand what it is biaxial. So this is nothing but the tau, and this is nothing but the sigma bending. Okay, so what happens, that this is the case of a biaxial stress system. And so what happens, biaxial stress system is that when we have two stresses acting at the outer surface, this stress and this stress, these are the two stresses that are acting out at the outer surface in two different directions. You can see the direction of the two stresses are in different axes. So this is the case of biaxial stress system. Biaxial stress system. Why? Because two types of two stress are acting at outer surface in two different directions. Okay. So this was the case, that sigma b and tau. Okay. These are two types of stress. Okay. So what will happen when this system happens, that when the case is of biaxial stress system? So what we will do, we are going to using maximum principal stress theory. So by using maximum principal stress theory we can find sigma n, that is normal stress. So for this we have got the formula, that is sigma n max is equals to sigma by 2 plus under root sigma by 2 to the power 2 plus tau. So this was the formula for the Nmax, now Nmax, and so we have got the equation for the sigma. This one is the equation, and this one is the equation for the shear stress. And once we are going to put, so putting the value of tau and sigma b in equation number third, we get what? Sigma and max is equals to, what is this sigma? That is 32m by pi d cube into 2 plus this one, that is 32m pi d cube into 2 to the power 2 plus 16t upon pi d cube, pi d cube to the power 2. This was the formula, and once we have put the value of sigma b and tau in this formula, we get something like this. Okay, so sigma n max is equals to 16m pi d cube plus under root 16m pi d cube plus 16t pi d. This thing we are getting from. So sigma n max is equals to, what will happen from this calculating, then sigma, this one will be what, 16m upon pi d cube plus, if you take the common here, 16 pi d cube under root m square plus t square. This thing we are getting here. Okay, so again we are taking the common from here, that is nothing but the sigma n max is equals to 16 upon pi d cube m plus under root m square plus t square. And so T equivalent is nothing but this formula. If we consider this formula, then what we will be getting here, that T equivalent, we have got the T equivalent is equals to under root m square plus t square. So we are putting the value of T equivalent in this equation, and the equation will become something like this, that sigma n max is equals to 16 pi d cube m plus te. This thing we are getting here. Okay, so let it be equation number 4. So in equation number 4, what we will do, so by dividing equation number 4 by this one 4 Roman number by 4 by 2 both sides. So my equation was something like this, that equation. Okay, so what was the equation? If we solve here, then what will be there? This is the equation, and so from here we can calculate it, that from this equation, that sigma n max into pi d cube upon 16 is equals to m plus t. This will be the equation. Now from here, this equation is similarly simplified into this way, and this will be my equation number 4. So yeah, so by dividing equation number 4 both sides, what we will get? We are getting that the sigma n max into pi d cube by 2 is equal to m plus Te upon 2. And so, what is this? Sigma n max. Sigma f max into pi d cube upon 32 is equal to m plus Te upon 2. This thing we are getting, and this is nothing but the m equivalent. This m plus Te by 2 is nothing but m equivalent. M equivalent. Okay, so what we can write from here, that m equivalent is equal to pi by 32 into sigma n max into what? That d cube. This d cube, and this will be equation number 5. So from here, what we have got, that's m equivalent is nothing but the pi by 32 into sigma n max into d cube, where this sigma n max is nothing but the normal, maximum normal stress, and this is nothing but the diameter of the shaft, and this m equivalent is nothing but the equivalent bending moment. Okay, m equivalent is nothing but the equivalent bending moment, m equivalent, and the sigma n max is maximum normal shear stress. And this d is nothing but dia of shaft, that is a solid shaft. So similarly, what we can do, that the similarly we can calculate what? Similarly we can calculate tau max by using principal stress theory, which is nothing but tau max is equal to under root sigma by 2 square plus tau square. This was the formula, and so tau max is equal to the value of sigma b and tau we will be going to put here, that is 32m by pi d cube into 2 divided to the power 2 plus is 16t upon pi d cube to the power 2. So tau max is equal to, what will happen? Once we are getting here this 16m by pi d cube to the power 2 plus this 16t by pi d. This is a simplified form, so no need to worry about that. Okay, this one we are getting here, and so tau max is equal to, once we take out the common, that is 16 pi d cube under root, that is nothing but the m square plus t square, and as we have derived earlier, that the tau t equivalent is nothing but the this t equivalent is equal to under root m square plus t square. So once we are getting to put here, then t max is equal to 16 by pi d cube, that is what? 16 by pi d cube into this Te. So this thing we are getting here. So then Te will be what? This Te equal to tau max into pi d cube upon 16. So this will be the formula for solid shaft. This will be the formula for solid shaft. And so for the hollow shaft, what will be the formula? This was the formula for solid shaft. And for hollow shaft, hollow shaft, what will be the formula? So we have to just the hollow shaft, we have got the two diameters, so putting in that formula only, we will be getting what? That is M equivalent is equals to pi by 32 into sigma n max into that d1 raised to the power cube 1 minus d2 upon what? d1 raised to the power 4. This one we are getting here only. And so similarly, this T equivalent will be what? Pi by 16 into tau max into what? d1 raised to the power cube 1 minus d2 upon d1 raised to the power 4. Raised to the power 2, sorry, not 4. Where d is what? Where this d1 and d2 is diameter of, this is the outer diameter, outer dia, and this is inner dia. So in this way we have designed the shaft subjected to the bending and twisting moment, and we have seen the case for the hollow shaft, and I hope that you all have understood this, and if any problem occurs you can ask me about these derivations regarding this particular lecture. Thank you all for watching this video, and if you like it, then please share and subscribe it. Thank you and good night.